Today we are going to see a topic singular value decomposition. It is again very important topic in data science. So in short we call it as SVD. Singular value decomposition is a technique used to decompose or factorize a matrix. So we already have studied about matrices. So matrix means it will have some collection of numbers, right? So matrices are not merely just a table of numbers. It carries a lot of information which may not be easily understood by humans, but the numbers in the matrix corresponds to different informations or hidden patterns. Okay, mathematical techniques like SVD help us to extract and represent these hidden patterns or features within a matrix. So basic idea is that from one matrix we can derive many useful mathematical properties and transformations, and SVD is one of the technique which is used to decompose the matrix to identify these patterns. Now, it is a powerful linear algebra technique which breaks the matrix into three different components. Okay, so mathematically it is represented as U, sigma, and V raised to t. The single matrix, original matrix, is broken into three different matrices that is represented as U, sigma, and V raised to t. So some of the applications of singular value decomposition is dimensionality reduction, noise reduction, and recommendation systems. So how SVD works mathematically? So as we told, an original matrix of size some m is m by n. Okay, that is m rows and n columns. A matrix A of m rows and m columns can be factorized or can be divided into three. That is u, sigma, and v raised to t. So first of all, what is v raised to t? Let us look. It is right singular vectors. So here we identify the relationship between the features, input features or the columns and some hidden patterns. Okay, we identify how the input features are actually related to these hidden patterns or hidden component that we are mathematical component that we are going to find. Okay, so that is v raised to t right singular matrix. It's a transpose of an n by n orthogonal matrix representing the relationship between columns and those same hidden concepts. Next comes the singular values represented by sigma. It is an m by n diagonal matrix. Okay, it's a diagonal matrix with non-negative real numbers, and it is sorted from largest to smallest. So when we are doing the numericals, you will be very much clear with what these things are. But now let us go into the theory portion. So it's a diagonal matrix. So in the diagonal portion, we'll have non-negative numbers, and that also is sorted from largest to smallest. It shows the strength or importance of each hidden feature. From this v raised to t, we will find some hidden features, and this singular value sigma will tell us how important these hidden features are. Okay, and this u is known as the left singular matrix. Again, it is an m by m orthogonal matrix. Okay, it represents a relationship between the rows and hidden concepts, such as how much related each row is to the hidden pattern or the component that we have found out. So this is singular value decomposition. So any m by n matrix is divided into three components, u, sigma, and v raised to t, where v raised to t is known as a right singular matrix. It finds out the relationship between the input features and the hidden concepts. Again, sigma, the singular values, is a m by n diagonal matrix. It shows the strength or the importance of each hidden feature that we have found or the model has found. Again, this u will represent left singular matrix. It's an m by n m orthogonal matrix which shows the relationship between the rows or the samples and the hidden concepts. Okay, so you have to study the dimension of each matrices. That v raised to t is n by n, and sigma is m by m, and u is m by m. Okay, so that is the mathematical definition of SVD. It is used in dimensionality reduction, recommendation systems, noise reduction, image compression. That is, dimensionality reduction means suppose you have four input features. Okay, maybe you have name, age, roll number, marks, and if you want to find the performance of students, then the age and roll number may not be that important. In that case, you can avoid those features and keep only the most important features, right? So the four-dimensional matrix or the 4D space may be converted to 2D. Suppose you are keeping only name and marks, then it is converted to a lower dimension. So for that, we can use SVD. So dimensionality reduction is an application of SVD. Again, recommendation systems. That is, suppose we have a matrix of people who watch Netflix and all, and suppose that matrix carries the information of how many times or what sort of movies are watched by each user. Then by uncovering these hidden patterns, we understand what the type of movies the user wish to watch, and we can identify this pattern and recommend the uh, similar kind of movies to the users. So again, that is next type of application or the area where we can apply SVD to. Next is noise reduction and image compression. That is like, suppose you assume your image is stored as images are always stored as pixels, right? Suppose we have pixels of some 1,000 pixels are used to store an image. Suppose assume that using 800 pixels, if you are able to represent the same image, or if you are able to reconstruct the same image instead of 1,000 pixels, then we see that there is a reduction of pixels, right? The storage required is less. So what we can do is we can compress the image using the 800 pixels. Okay, that is also carried out by what? This SVD. Okay, here we use the singular values and then we compress the images. So again, noise reduction and image compression is again another application of SVD. Now we'll understand SVD through some examples. So before going to mathematical calculation, we'll try to understand the basic idea of SVD using a very small example. Okay, consider the example here given here. Suppose we have the marks of two students in two subjects. Okay, marks of two students in two subjects, that is mathematics and science. So here the first row will indicate the details of first student, second row will indicate the details of second student. First student has scored 90 marks in mathematics and 80 marks in science, and the second student has scored 60 marks in mathematics and 50 marks in science. So we can represent the information as a matrix as given here. You can see A is equal to 90, 80 and 60, 70. Here the first row represents the student 1 and the second row of the matrix represents student 2. Similarly, the first column represents the mathematics marks and second column represents what? Science marks, right? So in a data matrix, we can generally think of rows as samples or observations and the columns as features or variables. Okay, so in this example, students are our samples and mathematics and science are our features. Okay, this is how we normally represent data in data science as a matrix. Now, what we are trying to understand actually, now once we have this data matrix uh, or a data set, once we have a data set, we want to identify whether there are any important structures or patterns in it, right? For example, we may notice that the student who score uh, high marks in mathematics also tend to score high marks in science, right? So likewise, we'll using this matrix, we are trying to identify whether any important patterns are there in this data. So we may also want to know whether the data can be represented using fewer dimensions or fewer components without losing too much important information. Okay, so this is where SVD becomes useful. So the SVD actually decomposes our original matrix into three matrices as told earlier, okay, into U, sigma and V transpose. So instead of looking at the original matrix directly, SVD gives us three mathematical components, that is three mathematical components that together can reconstruct the original matrix. Now, what does pattern mean here? So before we continue, let us understand what we mean when we use the word pattern. We can mathematically represent a direction that combines these two features. Okay. For example, the possible mathematical direction could be like we may have a vector with values zero point 0.7 and zero point 0.7. So this can be thought of as a mathematical combination of mathematics and science. Okay, mathematical combination of mathematics and science, or in simple terms we can write it as zero point 0.7 times mathematics plus zero point 0.7 times science. Okay, so this direction may represent something like overall academic performance, because both mathematics and science are contributing positively to this. So therefore we can say that this may be a direction of overall academic performance. Okay. So, but there is one important point here, like SVD itself does not look at the data and say like this is the overall academic performance. No, it's not like that. It only gives us some mathematical directions or some components. Okay. So we as data scientists interpret that mathematical component based on what the original features actually represent. So SVD doesn't give us a pattern exactly, doesn't give us overall academic performance. Instead, it will give a mathematical formula like this, and we should interpret it based on the meaning of features or input variables that we are taking. Okay. So when we talk about a pattern in SVD, we are usually referring to an underlying mathematical component or some formulas like this or a structure like this that we can interpret from the data. Okay, so that is a pattern. So we usually doesn't use the term pattern, instead we use the term mathematical component. Now, Now let us move on from our original features to these new mathematical components. Okay, so original features was what mathematics and science, but now we got, after computing the right singular vectors, that is v raised to t, we get some mathematical directions or components. So when it is a 2 by 2 matrix, you will get v raised to t as some v1 and v2. Okay, two vectors, you will get v1 and v2. So that is, we suppose assume that we got a matrix for v1 as vector like 0 0.7 0 0.7, and for v2 we got 0.7 and minus 0.7. Our interpretation is that here we have, suppose after computing the v raised to t or the right singular vectors, we got something like this. V is equal to something like this. So it shows that the two features are contributing in a positive direction. Okay, this is 0.7 first vector. Consider the v1, that is 0 0.7 0 0.7. This shows that two features are contributing in a positive direction. Okay, and we may consider it as a mathematical direction also. Okay, or overall academic performance direction. Now consider the second direction, that is 0 0.7 and minus 0.7. Okay, where mathematics has a positive coefficient and the science is having a negative coefficient. Okay, this indicates that this is the value of what science, and this is the value of, this is the value of mathematics, and this is the value of science. Okay, and this is also the value of mathematics, and this corresponds to value of science. So here science, in the second vector we can see that science is having a negative coefficient, right? So this represents a different direction. So this v1 represents one direction and this v2 represents another direction, or a mathematical component, or maybe in generalized way we can see, tell it is a pattern or some hidden concepts that we derived from the matrix. Okay, the first component represents positive direction and the next component may be representing a different direction. Now In our original matrix, the first column was mathematics marks and the second column was science. But after calculating V, its column represents new mathematical directions or components based on the original features. That is why I told like this is first column corresponds to max and this is science and this corresponds to another direction. Second column corresponds to another direction or another hidden concept. The first 0.7 in the second column corresponds to max and minus 0.7 corresponds to science. Okay. So original matrix contains our original features. The matrix V contains the mathematical directions formed using those features. This is one of the important concepts to understand before we start the numerical calculation of SVD. So how do we find this V? So we don't simply guess these mathematical directions. Instead, they are calculated mathematically. So what are the mathematical steps to calculate it? The first, we have to take our original matrix and then we have to find the transpose, that is A transpose, then multiply A transpose with A, okay, and find eigenvalues of A transpose A, then find eigenvectors of A transpose A. Again, you have to normalize the eigenvectors or find the unit length vector. Okay, so normalized eigenvectors becomes the columns of V. So that is the how you find V. Now, next is what are singular values? Singular values means sigma. Okay, the matrix is split into three. First we computed V and next we are going to compute the singular values. So how these are calculated? While finding the eigenvalues, so when finding the eigenvalues of A transpose A, okay, while finding values of eigenvalues of A transpose A, suppose we get two eigenvalues lambda 1 and lambda 2 as given. Okay, the singular values are obtained by taking the square root of these eigenvalues. So sigma 1 is the square root of lambda 1 and sigma 2 is the square root of lambda 2. So these singular values are placed in a diagonal matrix sigma. Okay, you can see sigma 1, sigma 2. And there is an important point to remember here, that is singular values are not the same as eigenvalues. They are actually square root of what eigenvalues, and that also here we have to arrange this in descending order. Suppose sigma 1 when you computed you got the value 10 and sigma 2 you got the value of 5. Okay, so you can see that sigma 1 is having the value 5 and sigma 2 is having sigma 1 is having value 10 and sigma 2 is having the value 5. So 10 is greater than 5, therefore you can keep 10 as sigma 1 and then you can keep 5 as sigma 2. Suppose it was the reverse, like sigma 1 when you computed lambda 1 square root of lambda 1 you computed you got 5 and square root of lambda 2 if you're getting 10. Okay, then when you place that in sigma in the singular value matrix, then you have to arrange it in descending order. That is sigma 1 should have the higher value, that is what sigma 1 should be 10 and sigma 2 should be given as 5. So that is the important point that you have to remember when you are constructing the singular value matrix. You should arrange the sigma 1 and sigma 2 according to descending order. Now, what do this singular value actually tells us? So, in when we found the right singular matrix V, I told you that we find the underlying concepts or the different directions corresponding to these underlying hidden patterns or hidden concepts, right? So, we have V1 is a gives corresponds to one direction or one hidden concept. V2 corresponds to some other hidden concept. So this value of the singular value tells us that, okay, sigma 1 corresponds to V1 and sigma 2 corresponds to V2. It tells us that the V1, okay, the direction of the mathematical component V1 uh, is having some larger contribution, okay, or it is the most important direction when compared to V2. Okay, since sigma 1 and sigma 2 they are arranged in descending order, sigma 1 is having higher value, right? It shows the strength or the importance of the direction that we have found. So it tells us that since sigma 1 is larger when compared to sigma 2 and sigma 1 corresponds to V1, it tells us that yes, this V1 that we have found is having higher importance, or it is a higher it is an important underlying concept which is used to reconstruct the original matrix that we have decomposed. Okay, or this is the most important pattern that we have found. Now the second most important main pattern that we have found is V2. Okay, so that is the importance of singular values. It tells us how important the directions we have found are. Okay, so that is the importance of singular values. Now next is, what is the component U in the SVD? So after finding V, then we found sigma. Now last we are going to find U. So U equal to, we have a formula for computing U. Okay, U is equal to A P of I by sigma I. So Vi is the ith column of V. Sigma corresponds to singular value. Okay, and Ui corresponding to the resulting left singular matrix. The columns of U represent how the samples, here in our case of students, are represented with respect to the corresponding components, or the each column of U corresponds to how each student is related to this direction, or how each observation can be represented using the patterns that we have found. Okay, that is the meaning of U actually. Let's look into U with the example of students. Okay, suppose our data set has some 4 students. Okay, suppose a data set has 4 students. The matrix of you will have 4 rows. Okay, suppose we are having 2 students, means our matrix you will have uh, 2 rows. Okay, so here the first, this point 8. Okay, so this point 8 corresponds to first student, and this point 6 corresponds to second student, and this entire column corresponds to the first direction or the hidden pattern that we have found, that is V1. Okay, and this corresponds to, this entire column corresponds to the second direction that we have found. And what does this point 6 represents? How our first user or a first student, suppose it is S1, first student, how it is related to the second direction or the pattern that we have found, and this indicates that how our second student is related to the second direction that we have found. Okay, from this what we can understand, the first user is strongly associated with the V1 or the first direction that we have found, because it is point 8. Here with the second direction it is related point 6. So first user is point 0.8 times related to the direction that we have found, right? That is the meaning of U. How much our observation or samples are related to the components or the hidden patterns or the mathematical directions that we have found. Okay, so that is the meaning of U. So student 1 is represented with to component 1.8, and student 2 is associated 0.6. Okay, with the first direction. Likewise with the second direction, student 1 is associated with zero point 0.6 and student 2 is associated with minus 0.8 with the directions that we have found. Okay, so what is the complete meaning? So for each component, okay, for every component we have 3 corresponding elements. First we have Vi, then we have sigma I, and then we have Ui. Sigma, this Vi, indicates what is a mathematical direction or what are the underlying patterns, and sigma A tells us how strongly does this component contribute to, or which component is having higher importance, that is given by sigma I or the singular values matrix, and ui shows how are the samples represented with respect to this component. So these are the three things that SVD tells us. So connecting to our student example, so our original matrix contains the mathematics and science marks. Okay, so these are our original features. And when we apply SVD, we decompose this matrix into A is equal to U sigma and V raised to T. So the original data can be represented as the product of sample representation U, component strength sigma, and feature directions, that is V raised to T. So when you multiply all these three together, you will get an approximation of original data. Maybe the exact values may not be got, but the values that is very much similar to your original data will be got after you are multiplying all these three components. Okay, so consider this student marks. That is, we have the marks of. Again, here we have three students and three features: mathematics, science, and English. So maybe this matrix will be divided into three, that is U sigma and V raised to T. And maybe in V raised to T we'll find three different directions, and we will have three different singular values. And based on it, we'll identify which is the most important feature. And after we have found out that, we'll find the matrix U, which shows how these samples are related to these three components. So that is the basic idea of SVD.